Okay, so, right, so, in some sense, this course is like calculus revisited. Right, we're going back to calculus and trying to justify everything rigorously. And so now we're going into chapter 5. So this is sort of like return to differential calculus. Right, so all the results that you know from differential calculus, we'll put them on a secure footing. Okay, so okay, so of course we should start off with the idea of the derivative. So definition. We have some function. Let's say it's on a closed interval, and we want to say we have some point x is in the open interval AB, and we want to say that the function is differentiable at that point. Anybody remember how you define the derivative? What's a derivative? Right, you have some function, right? You have some point x, and you define this thing called the derivative. Anybody remember what a derivative is? How you define it? Yes, Anne, go ahead.
It's the limit as h approaches x of f at h minus f at x over h minus x.
Sure, great. Yeah, I'm going to use a t.
Okay.
Normally people use h. People usually use h for a difference, so they'll call this thing x plus h. And then, so you could just as well define it as the limit as h goes to 0 of f of x plus h minus f of x over h, right? Where h designates the difference between these 2 points. It's of course absolutely the same thing to say that you take a second point t. You take the difference between the difference in height between those 2 points, and then divide by the width here, right? That's exactly the same thing. Okay, so right, so right, so if, and we'll write these in both ways. If this limit exists, we say f is differentiable x, and call the limit f prime of x. Right. So you all know that, right? So you take the second point, and then you take the slope of the line. Right. You took the slope of this line through these 2 points, the slope of the secant line, right? And then you let the second point approach the first point, right? You let t approach x, right? So you take the limit of the slopes of the secant lines as the second point approaches x, right? And that gives you the slope of the so-called tangent line. Okay. So right. So that's how derivative was defined back in calculus. It will be useful to think in the following way. So you say, well, f differentiable at x is the same thing as saying that there exists some number f prime x such that the limit of f of this thing minus f prime x equals 0. Okay, as t approaches x. Okay, that's exactly the same thing, of course, right? Right. Let me make sure I get this right. Okay, so okay, let me denote this thing by u of t. Okay, so this is some function. This whole thing here, I'm going to call u of t. Okay, so another way of saying this is that there exists an f prime and a function u of t such that f of t minus f of x over t minus x equals f prime x plus u of t. And the limit of u of t as t goes to x is 0. Okay, maybe it's a little bit better narrative to say there exists this function u of t such that the limit of u of t is 0 as t approaches x, and this thing happens. Okay, so differentiability is the same thing as there exists the existence of some number and some function that goes to 0. Some function that goes to 0 as t goes to x, such that this thing is true. Okay, right? I hope you see that I'm not saying anything new at all. Right? I'm just relabeling things. Okay, right. What function is u of t? Of course, u of t is equal to this minus this, right? You can figure out what u of t is. It's not some mysterious function. It is literally, this, right? You can see from the equation, right? U of t is defined. You know what u of t is. Okay. Okay. So another way of saying it is to say that again, there exists some function, and I'm sorry, there exists some value and some function u of t such that right, the limit of u of t equals 0 as t approaches x, and I'm not going to do anything special here. This thing equals f prime of x times f prime of x times t minus x plus u of t times t minus x. Okay, so I'm just multiplying through by t minus x. Actually, let me move the f of x to the other side. Right, so I have minus f of x. I'm just going to add f of x to the other side. Okay. Okay, so we've taken our regular definition of differentiability and just rearranged it a little bit. Okay, and now I wonder if people recognize what's going on here. So a function is differentiable. What we're saying is that a function is differentiable at x if so our variable is t. If f of t equals something plus this thing that vanishes as t goes to x. Okay, so notice that this thing over here vanishes as t goes to x, right? U of t is that function that vanishes as t goes to x. In fact, it vanishes in a kind of double way, right? Because this thing goes to 0, and this thing goes to 0. So this thing here vanishes as t goes to x, even if you divide it by t minus x, right? So like it very, very strongly goes to 0. Okay. Okay. Now, what's this thing here? Anybody recognize this thing? What is this thing? F of x plus f prime x times t minus x.
kind of looks like product rule.
No. No. Anne, what do you think?
The tangent line?
It's the tangent line. It's the equation. This is the formula for the tangent line, right? If I call this thing L of t, think of what it does, right? When L is x, L of x is going to give me f of x, right? L of x is going to give me f of x, right there, right? And then as you move farther away, you're gonna add on, the distance. If my t is some other point here, I'm going to take that distance and multiply by the slope, right? I'm going to multiply by the derivative there, and I'm going to add that thing on, right? Well, that's exactly the equation for the tangent line, right? So, so this thing here is the linearization of f, right, at x, right? Okay, the thing that has the tangent line as its graph, right? Or just call it the tangent line. Okay. Okay. So now think, what does differentiability mean? So this gives us actually a superior way of thinking about differentiability. Differentiability, yeah, right? Like it's the the limit of the slopes of the secant lines. Differentiable means that if you take the limit of the slopes of the secant lines, you get a limit. You get an actual number here. But actually, what it really means, or equivalently, and even better way of viewing it, what does differentiability mean? It means that your function can be written as the tangent line plus something that vanishes as t goes to x. Okay? So you think of this thing as some sort of error. Okay? Your function is basically a tangent line. Your function is basically a tangent line plus some sort of error. But that error vanishes as you get close to x. In fact, it vanishes in a really strong way. Okay? So what does differentiability mean? It means that your function at x, what does differentiability at x mean? It means that your function at x is basically a line. Okay, it's basically a line, right? So your function is a line, and it's plus some error that vanishes very strongly as you get close to x. Okay, so in other words, whenever you have a function that's differentiable somewhere, right? If this function is differentiable here, what that means is that as I zoom in, right? The function may not look like a line at all, but as I zoom in closer and closer, it's going to look more and more like a line, right? So the closer you get in, the more line-like it gets. Okay, you're guaranteed that your function is basically a line. Okay. Okay. So this is kind of like the right way to think about differentiability. Okay. Okay. So now we're going to prove some. We're going to basically recreate all of your knowledge of differential calculus, maybe in this class. Okay, we'll see. I don't think we'll get all of them, but we'll get a whole bunch of them. So first off, kind of a standard theorem from calculus that differentiable at x implies continuous at x. Right? Differentiable at x implies continuous at x. Okay, so you have some function. Say some function on AB into R. X is in the interior, and you want to show that if f is differentiable at x, then it's continuous there. Okay. So the standard proof that's given in most calculus textbooks is as follows. You say, well, look, differentiable means that the limit of f of t minus f of x over t minus x as t approaches x equals f prime x, right? And then you say, then you multiply both sides by the limit of t minus x as t approaches x. Okay. So you get this sort of thing. Right, so you get this sort of thing. Okay, and then you use the fact that if this limit and this limit exist, then the product of the limits is the limit of the products, right? So like if you have two functions, if the limit of f of x is a and the limit of g of x is b, then the limit of f times g is going to be a times b, right? So you say, well, look, this limit is something, this limit is something, so the product of the limits, the product of those limits is going to be the limit of the product. But the product here is going to be t minus x times f of t minus f of x over t minus x. And those things cancel off, and I get this thing, right? So the product of the limit is the limit of the product, and you get this thing. Now this thing on the right is just a constant times this, which is 0, right? As t goes to x, t minus x goes to 0. So you get 0, right? So what does that tell you? That tells you that the limit as t goes to x of f of t minus f of x is 0, but that's the same thing as saying that the limit of f of t is f of x as t goes to x, and that's continuity, right? That's how we defined, that's what we saw as continuity. Okay, so that's kind of like the standard proof that people give in calculus classes. Okay, to show that differentiability implies continuity. Okay, but I find this proof really, really unintuitive, right? It's sort of like algebraic magic, right? You just like multiply two things together and then bang, you know, this thing comes out. Okay, so rather than think like that, I think it's much better to use this way of thinking about differentiability. Right? This way is far more intuitive because it says your function is basically a line, right? And lines are continuous. So, you know, like the intuition is, you know, your function, as you get closer and closer to the point, your function basically turns into a line. And lines are continuous. Done. Okay, so that's the idea. And so, different proof, right? You say, well, differentiable at x means that f of t equals f of x plus f prime x t minus x plus the error, right? For some function u that goes to 0. As t goes to x, right? So we just saw that, right? Differentiability means that you are a line plus some error that goes to 0, that strongly goes to 0. Okay, so the limit of f of t as t goes to x is the limit as t goes to x of this thing on the right hand side, right? Of this thing here. Okay. Well, what happens to that? What happens to f of x as t goes to x? T is moving. What happens to f of x? Well, nothing, right? F of x is a constant, right? You get f of x. What happens to this thing as t goes to x?
It approaches 0.
Goes to 0, right? Because this is a constant, a multiplied by something that goes to 0, right? What happens to this thing as t goes to to x. Say it.
Oh.
It also goes to 0, right? Because this goes to 0, and then this also goes to 0. It's 0 times 0, very much 0. Okay, it's a very 0. Okay, right? Plus 0 squared. Okay, okay, and you're done. Right, right. The limit of f of t as t goes to x is f of x. That's continuity. Okay, so I don't know which way you like better. I like this way better by far, because this is just algebraic trickery. And this actually shows that you understand what the derivative is, what differentiation means, what differentiability means. Okay. Okay, so your first bit of calculus knowledge, differential calculus knowledge, has been recreated. Okay, now we're going to go for your standard rules of differentiation and arithmetic. Okay, so again, you have some functions. So f and g are continuous, nope, are differentiable at some point x in the interior, AB. Okay. Then when the derivative of the sum is going to be the sum of the derivatives. Right, you can add functions and then differentiate them, or you can differentiate them first and then add them. It doesn't matter, right? Those operations commute, right? The order doesn't matter, right? Like you can go down the hall and up the stairs, or you can go up the stairs and down the hall, right? It's the same thing. Okay. Yeah. Second, of course, if you have a product and you differentiate it, right? You get the first guy times the derivative of the second guy, plus the first guy's derivative times the second guy. Right? 3, quotient rule. If you have a quotient and you differentiate it, right, you get, of course, the bottom times the derivative of the top, minus the top times the derivative of the bottom, over the bottom guy squared. Right? So quotient rule. So, right, so it's just some basic laws of how differentiation interacts with arithmetic. Okay. I'm not going to prove the first one. The first one is just just write it down. It's very straightforward. I'll do the second and the third. So prove the second one, right? So let's consider. Right, so we know that f and g are differentiable at x, and we want to look at, what should turn out to be f prime g. So f prime g is going to be, what's the definition? It's going to be f of, let me write this down. Yeah. So it's going to be f times g at t minus f times g at x over t minus x as t approaches x. Right? We're hoping that that limit exists. Right? We don't even know that that limit exists yet, but we're trying to show that that limit exists and equals this thing on the right here. Okay, so we're going to play a trick. So let me rewrite this. This is f of t times g of t minus f of x times g of x over t minus x. and we're going to play a trick, which is we're going to try and work in things that we know about. Okay, so right, we know about things like this: g of t minus g of x over t minus x. We know about things like right, because the functions are differentiable there at x. We know that these things are going to tend to limits. Okay, we know that these things are going to tend to limits, and so what we're going to do is sort of like slide them into what we have here. So what we're going to do here, say, is we'll subtract out f of t g of x, f of t times g of x. Okay, I hope you see why I'm doing that, because I'm kind of working in this g of t minus g of x over t minus x, right? Which is something I know about, right? Of course, I can't just throw that in because I feel like throwing it in. So let me add it back in. Okay, that's okay because I just added 0, right? So we slide in a cleverly chosen 0 that sort of gets us closer to things that we know. Okay. This is kind of a common tactic. Okay, so now let's simplify things. We say, well, look, this thing here I can rewrite as f of t times g of t minus g of x over t minus x, right? And this thing over here I can write as g of x times f of t minus f of x over t minus x. Right? So I've just taken these. I've just separated the fraction, right? And then factored out. I just distributed out some common terms. Okay. So now think. If we look at the limits of these guys, g of t minus g of x over t minus x as t approaches x, plus the limit of g of x times f of t minus f of x over t minus x as t approaches x. Right? If we look at those things, well, what happens to them, right? Let's look at this one first, right? What happens to this one? Well, g of x is our variable is t, right? So g of x is a constant, right? G of x is just a constant. I can pull that constant out, right? You can pull constants out of limits. So what I'm left with is the limit of this thing. Well, we know what that is, right? That's the derivative. Right. So this limit exists and equals this thing. Okay. Now let's come back to this guy. The limit of this thing is what? Of course, it's g prime, right? This thing goes to g prime of x. What about this thing? The limit of f of t as t goes to x. Charlotte?
F of x.
F of x, yeah. Why does it do that? How do we know that it turns into f of x? For what kind of functions does the limit of f of t turn into f of x? If your function is continuous, right? Do we know our function's continuous? Do we know that f is continuous?
By the last theorem.
By the last theorem. F was differentiable. Our previous theorem said differentiable implies continuous. So we're good. Right? So this does actually turn into f of x. We're good. Okay. So these limits exist, and so the sum of the limits equals the limit of the sums, right? The limit of the sums. So this thing actually does equal this thing. right? So if you have, limit of f of x is a, limit of g of x is b, then the limit of the sums equals the sum of the limits, right? So if the limits exist independently, then it's okay to do this sort of thing and say, if the limits exist independently, excuse me, then the sum of the limits equals the limit of the sums. So the sum of the limits equals the limit of the sums, and so we get that this thing equals that thing. Okay. How do you feel about that? It's good. It's okay. Okay. I wonder if we should do the quotient rule or not. The quotient rule, the proof of the quotient rule is like this, but just a little one step more more convoluted. It's just more algebra. It's the same idea though. It's the same idea. You're going to slide in something that makes things makes things work out for you. Do you guys want to see it, or it's just like this, but more so. Okay, we'll pass. Yeah. Yeah, I don't know if it would. It would sort of reinforce the idea of cleverly choosing a zero, sliding in a term that allows you to simplify what you've got. But you've seen the idea already in some sense. Yes.
This is a kind of random question.
Yeah.
But is there a rigorous proof for the power rule for derivatives, or is that just using the definition of the derivative?
For the power rule, yeah, there is. You have to. I mean, there's kind of two things that happen. For the case of x to the n, say, where n is a natural number, then you need to use a little bit of combinatorics, you need to use a little bit of combinatorics or induction to get it. It basically hinges on Pascal's triangle. Do you know this term, Pascal's triangle? So Pascal's triangle, in other words, some combinatorics. But yeah, everything can be proven. Yeah.
But not in this class.
Will we do? I don't think we'll do the proof in this class. Yeah. If you want, I can show it to you. Do you want to see it? Not now. Not later. Yeah, I mean, so later. I think later on. I don't think I actually covered it, but right, because the power rule, of course, is valid not just for natural numbers, but for real numbers. In that case, it's a little bit trickier, right? Because then, how do you define x to the r, right? Where r, when r is where r is some irrational number, right? How do you define it? That maybe you haven't thought about that, right? But the way to do it is to use the logarithm, and so in the section on the logarithm, I think Rudin actually proves the power rule, because you need to define the logarithm first in order to be able to prove the power rule. But the case of the natural numbers is actually relatively straightforward. Although you do have to use, properly speaking, you should use Pascal's triangle. Properly speaking, you should use some combinatorics to do it. Sometimes when I teach it in a Calc 1 class, I'll put up Pascal's triangle and see, Pascal's triangle says blah, blah, blah. But Pascal's triangle, you need to prove some stuff about it. Yeah, so it's what my friends in college would have called cheesing. That's cheesing the proof. There's a lot of cheese in that proof. I never use this term, but yeah. But it was a common slang among the math majors. Okay. So now let's go to the chain rule. So again, let me make sure I got everything proper. So you have some function f and it's continuous. You have some other function, g on some set from I into R, where I contains the image of f. Okay. Of course, you know the statement of the chain rule, right? If f is differentiable, at some point x and b, let me make it like this. If x is differentiable at some point in AB, and g is differentiable at f of x, then the composition is differentiable at x, and you know that the derivative is just the product of the derivatives at the appropriate points. Okay. Right, you know the chain rule. Okay. Okay, so the proof of this actually will use the sort of alternate view of the derivative, right? Basically, what we're going to say is that, you know, that g is line-like at f of x, and f is line-like at x, and then we'll see that that we'll be able to compose, because it's sort of like saying, you know, this works for lines, and so it's going to work for differentiable functions, right? Because differentiable functions are basically lines. That's really that's really what the chain rule says. What the proof of the chain rule is, that, you know, if you had lines and did this, it's definitely true. And so, right, if you had lines and composed them, then, you know, what happens? The derivative of the composition is just going to be the product of the slopes, right? You're just going to get another line that travels, you know, product of slopes fast, right? So, yeah, that's basically the proof of the chain rule. Okay, so you say, okay, well. Okay, so let's think of what we want to show. We want to show that, right? We want to show that this thing, that this thing equals this thing, right? So we want to show that the limit of g of f of t minus g of f of x over t minus x equals, you know, g prime f of x, f prime x, right? That's our goal, right? Okay, so let's consider g of, let's just consider the numerator here. Okay, just consider the numerator here. G of f of t minus g of f of x. Okay, and remember that g is differentiable at f of x, right? Which tells us that that if we look at, well, I just wrote it down. That this thing is going to be the, right? If we take this thing and divide by f of t minus f of x, we're going to get g prime at f of x plus some error term, right? Error term that depends on f of t, right? Right. This is, you know, this is what we're, you know, this is the right. Remember, g differentiable at this. Wait, let me write it like this. G differentiable at some point zeta means that g of t equals g of zeta plus g prime at zeta, t minus zeta plus the error term yeah, t minus zeta, right? this was the expressing the thing as the tangent line plus some error, right? So I'm going to go backwards a little bit, right? So I'm going to just write it like this: g of t minus g of zeta divided by t minus zeta equals g prime zeta plus nu prime zeta. Oh, sorry, this plus nu prime of t. Sorry, nu of z, nu of t. Okay, so I'm just stepping backwards from, this is where we ended up, but along the way we had this. Okay, and I'm just going to use this, right? So g of f of t minus g of f of x divided by this equals g prime at zeta plus nu at f of t. Okay. So yeah, and let me move this over to the right hand side. So g of f of t minus g of f of x equals f of t minus f of x times g prime f of x plus nu of f of t. Maybe I should just call that v. I'm not going to call it nu. Sorry, it's no longer the Greek letter nu. It's a v. Okay, because we used a u before for the error. Okay, I just need a different letter for the error because I need a letter for the error of g, and I need a letter for the error of f. And so I'm going to use u for f's error. I'm using v. Sorry, I should not have used nu. I'm using v for g's error. Okay, everybody on the same page, I hope? Okay. So what do we use? We use the fact that g is basically its tangent line near f of x, right? That we can express g as tangent line plus error. Okay, that's all we're doing here. Okay, that's all we've done. Now we come here. We say, well, we know that f is differentiable, right? F is differentiable at. Actually, let me rewrite this. G of t minus g of t minus g of zeta equals t minus zeta g prime zeta plus v of t. Okay. Just rewrite it. We have a similar thing for f, of course, right? F of t minus f of x equals t minus x f prime x plus u of t. Right? So I'm going to use that now, right? I've got f of t minus f of x here. I'm just going to substitute in the tangent line form for it. Okay. So we say, okay, well that's just t minus x times f prime x plus u of t times g prime f of x plus v of f of t. Okay. Right. Right, so like I said, we're just using the fact that each of these is a line, right? So this guy is a line. We use the fact that g is basically a line. Now we're using the fact that f is basically a line, right? Okay, so we put in the line forms, and you see, well, when I divide both sides by t minus x, right? What happens? Well, this thing just vanishes. Okay. Now, what did we want? We wanted to look at the limit as t goes to x of this thing, right? Well, the limit as t goes to x of this thing is the limit of this thing on the right-hand side, right? So let's look at it, right? Right, the limit as t goes to x of this thing on the right-hand side, well, we got f prime x plus u of t times g prime of f of x plus v of f of t. Right? Okay, so what happens, right? As t goes to x, well, f prime stays still, right? what happens to u of t as t goes to x? Goes to 0, right? That's that error thing, right? That goes to 0, right? As t goes to x, what happens to this thing? Nothing, right? As t goes to x, what happens to this thing? Well, we've got a composition. The limit of f of t as t goes to x, because f is continuous, right? We assume that f is continuous. That's going to be f of x, right? And we know that the limit of v, v of t as t goes to f of x. Maybe I should use a different variable. I'll use zeta. Right? The limit, for the g function, g was differentiable at f of x. Right? This is the error guide for g's tangent line. Right? As you get close to f of x, that thing goes to 0. Right? So now we've got the limit of something. The limit of f of t is f of x. The limit of this guy as zeta goes to f of x is 0. And so this composed limit is going to go to 0. The limit of this composition is going to go to 0 also. And lo and behold, you get f prime x, g prime f of x. Okay. Okay. So yeah, so that's the proof of the chain rule. And as you see, what we use is simply that g is a line and f is a line. Okay. Okay, I think that's a good place to stop actually. So let's stop there. Next time we're going to talk about like the rest of your differential calculus knowledge. In particular, we're going to talk about Rolle's theorem, Rolle's theorem, which says that whenever you have a function that's continuous on a closed and bounded interval and differentiable on the interior, then it will you're guaranteed a point where the derivative is 0, right? And then we'll talk about its relative, either its father or either its parent or its child, the mean value theorem, which says that whenever you have a function that looks something like this, then you're guaranteed a point where the derivative equals the slope through the slope of the secant line through the endpoints, right? And then we'll do something called the generalized mean value theorem, which involves two functions, and you can say something about there'll be some magical point where something amazing happens. Right. So these are all sort of like, if you have the setup, there's some point where something good happens, right? Yeah. So we'll talk about that. This one leads actually to the proof of L'Hopital's rule. Yeah. Okay. So that's it for today. I was talking with my daughter this morning about math, and I don't know, let me just say what I said to her. I think it might be useful. And I said that math is all about imagination, right? You sort of have to, like, everything you have to, there are these abstract things, and you try to, imagine exactly how they work, right? So like, there's differentiable function behaves like a line. And so you imagine if it is a line, then you have to sort of like bring things into your mind. And the bigger imagination you have, the easier things will be. The more you can bring into your mind, the more you can imagine, the more complicated things you can imagine, the easier things will be. Right? The easier it'll be to understand things. Because it's like you're studying animals that don't exist, but you have to, you ask questions about how they behave. right? And so you have to have in your mind some sort of model, an imagined model of how these things behave, right? And in some sense, that's how human beings deal with everything, even things that are real, like a cat, right? You have some model in your head about how the cat's going to behave, right? And that's how you understand the cat. But inside, what you have is still this mental construct, right? And so that's sort of what you want to do in math. And the people who are really good at math, are able to have like very, 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 very extensive models inside their head, right? So this is part of this course is to get you to increase your deepen your ability to imagine. Yeah. So I don't know if that's helpful, but that's what I told my daughter this morning.